Hello student to the course of Foundation of Classical Electrodynamics. So, today we have module 4 and in this module we have under this module in lecture 63 today we are going to learn the wave equation and then the Maxwell's equation. So, we have class number 63 today. So, before going to the Maxwell's equation, it is important that we should know about the wave equation. So, let us first discuss the wave equation. Just most of you may aware of the wave equation in different branches of physics. So, we will going to make a simple general discussion about the wave equation here. So, suppose I have a coordinate system like this which is fixed and I called it say O, and in this fixed coordinate system let me have a disturbance or a wave like this, and say this is z distance, this is z coordinate, along this direction is z, and the function that is distributed here is f. This point but let us define a point over this wave, say this one, and this point is having a coordinate here and this coordinate with respect to this is z, okay, and it is at time t equal to 0. So, whatever the function we are having here is f z at t equal to 0. Now, this wave is moving and at some different time t it is located at this place, and this is moving. So, this is the wave we are having, the same wave, and it is moving from this point to this point, and I am just concentrating on the point we marked here. And suppose this is a frame that is also moving in the same velocity of the wave. So, somebody who are in this frame O prime will going to see that there will be no change at all in the wave. So, he can also measure this coordinate, this point, and this coordinate that is simply, this is a prime frame. So, this will be simply z prime. Okay. Now, this is the same coordinate. So, I should write bracket z, and I should say that this is the coordinate with respect to the fixed frame, the same coordinate. So, it is measured from here to here, we measured this is a z coordinate. So, this should be the z same coordinate with respect to the fixed frame. So, this is coordinate z is a coordinate, should not write all this, I simply write coordinate with respect to the fixed frame. Fixed frame is here. So, now we just try to understand what is the coordinate, okay? I mean how the coordinates are related. So, if the velocity is v and if it is measured at time t, so this is say time equal to 0. So, this is at t equal to 0, this is at t equal to t. So, if the velocity is v, so I can have from here to here this distance, I can have it is simply v t. V is the velocity, and at time t this is moved to this place. Now, what is z prime if I want to find out in terms of z? So, this point is z, and from here to here it is z prime. So, eventually z is equal to z prime plus v t. This is, so z I am measuring the same coordinate with respect to this, and this is measured with respect to the frame that is fixed. So, it should be z. So, z should be z prime plus v t. The v is the velocity of the frame. So, the frame is moving, or v is the velocity of the wave itself. So, wave is moving with this velocity v, which is fixed. Okay, this is now I can have the function here. So, the function of z, this is the same point that we are having at z prime. So, these two things are eventually same. Now, z prime, if I write, it should be simply z minus v t. So, for a moving wave, we have an interesting relation that for a moving wave, for a moving wave, we simply have f z is equal to f of z minus v t. So, the z coordinate and t coordinate can be written together like z minus v t form, and that tells me that the wave is moving. That is a some sort of indication. Now, we know the wave equation, several places we find it. So, the wave equation simply I can write in 3D, it should be something like this. This is a differential equation or two variable differential equation, and this is nothing but the wave equation in 3D. In 1D, the wave equation simplifies. For example, this is the 1D problem, the figure I just mentioned here. In one dimensional problem, we can simply have the expression like d2 psi d z square, that should equal to 1 divided by v square d2 psi dt square. This is in 1D. Now, the solution of this equation that we are looking for, the solution is of the form, solution of such differential equation should have an interesting form, and the solution should have a form like f. Okay, I used f, so better I just replace this to f, not psi, because I used a function f. So, it should be like f. So, f z t at any point z and t, that I can write a compact way like a function z z minus Vt. Instead of writing Zt separately, I can write in a compact way Z minus Vt, and that tells me that this is a solution. I said I can write it this variable, I simply write Gm, say, where my m is Z minus Vt. So, I can have from here, I can have a relation that Gm dz equal to 1 and del m del t equal to minus of V. That two information we are having, that we are going to exploit later. Now, if I demand that this should be a solution, then I just simply check it, because we know f is a solution. So, I just replace like d2f dz square, that quantity I simply have d dz of df dz, and df dz I use the chain rule d dz, because if I am going to use these things Gm, so I should have like d of g dm and dm dz. So, this simply I have d dz, this quantity is 1. So, I should have dg dm. This again I can use like d of dm of dg dm and then dm dz. So, this quantity eventually is d2g dm square. Okay. So, I have d2f dz square is equivalent to this quantity. In a similar way, now we will check that what we have for the time derivative. So, let us do that. So, I have d2f dt square. So, that quantity if I want to calculate, because that is in the right hand side we are having here in the wave equation. So, that quantity again in the previous way I have d dt of dg dm and dm dt. G is a function of m, so I can have a partial derivative. So, this quantity dm dt we know it is minus v. So, I have minus of v d dt of dg dm. Further I can have minus v d of dm dg dm and dm dt, chain rule dt. So, this again gives a minus v. So, eventually I have v square d2g dm square. So, now I can see that 1 divided by v square d2f dt square is something like d2g dm square, which is d2f dz square. That means that Gm is a solution, because when I put Gm here in this equation, it basically satisfies this equation 1 divided by v square d2f dt square is the same value of 1 d2f dg square when I put f as a the solution as gm, where m the argument is written in this form z minus vt. So, we can conclude that gm which is equal to g z minus vt, this form, is a solution of the wave equation of the wave equation and the most general solution, because in the similar way, if the wave is moving in not in the right hand side, but the left hand side with a negative velocity, then I should have another solution. So, for negative v, that is moving in the opposite direction, I should have another solution which is g is equal to z plus vt. Just replace the sign of the v, because now the wave is moving in opposite direction. So, in general, I can have a general a superposition of these two solution can be the most general solution. So, the most general solution can be written as the most general solution of the wave equation one can write as a constant C1 g of z minus Vt plus C2 g of z plus Vt. This should be the most general solution of the wave equation, but the interesting fact is that the solution can always be written like z minus Vt or z plus Vt. Z and t can be written in a same footing like z minus Vt or z plus Vt. So, this is the signature of a solution that should satisfy this wave equation. So, whenever you have this kind of solution, then readily you can understand that this is a solution for some wave equation. Okay, so we have a very rough idea about the wave equation and solutions, and we will going to use this concept in Maxwell's equation when we derive the Maxwell's solution. So, let us now directly jump to the Maxwell's equation, a very important topic in electrodynamics. So, we are going to start this topic today. So, the topic is Maxwell's equation. Okay. So, one by one I should write. All the equations are well known. The first equation that we find in electrostatic, that divergence of E is rho by epsilon 0. This is Gauss's law. This is our first Maxwell's equation. What is next? Next is curl divergence of B is equal to 0. That we find in magnetostatic, one of the fundamental equations, and that tells us that the magnetic monopole does not exist. That is the physical understanding of this. Then we have third equation, curl cross E is equal to minus of del B del T. That is our Faraday's law. This is the first time we have a relationship with E and B. First two equation, the first equation from electrostatic, second equation is from magnetostatic, third equation we find the first time there is a relationship between E and B, and now we are entering in the domain of electromagnetism. So, here this is our Faraday's law. And finally, the fourth equation that we got in magnetostatic, that is curl cross B is mu 0 j up to this, and that we mention that this is Ampere's law. So, these are the four laws we are having, not four laws, three laws are there and one some sort of identity we had. So, two equations related to the divergence and two equations related to the curl of electric field and magnetic field respectively. So, now what we do, that we will check few things. So, after having this equation, now we are in a position, the four equations are there in my hand. So, we can check few things. So, from equation 3, so first thing we check is from equation 3 what we get. I can have the divergence of the curl of E if I make the divergence of the curl of E, then this side should be 0 and this condition should be reflected in the right hand side as well. So, if I do, I will get like it is divergence of in the right hand side from equation 3, it is minus del B del T, and that I can write at minus of del T and divergence of B. I can exchange this operator because they are independent, but this quantity is 0. So, I can have the left hand side. So, I should write, so this quantity is 0. So, the left hand side is always 0 because I am taking a curl, divergence of curl of something. So, it has to be 0. So, left hand side is always 0 and right hand side, so far reciprocate well, is also always 0. So, there is no problem with these two equations. Now, let us do the same thing for equation 4. So, this is from equation 3. So, from equation 4 what we get? From equation 4, if I do the same treatment, like let us take a divergence of curl of B. So, the left hand side again should be always 0 unconditionally. What is the right hand side? Right hand side we have mu 0 and then divergence of J. Now here we are having some issues because left hand side is always 0. Left hand side is always 0. This is unconditional, because if I make a divergence of a curl of something, then it has to be 0. But what about the right hand side? Whereas the right hand side is not always 0. For steady condition maybe it is 0, but this is not always 0, but left hand side is unconditionally 0. So, what is the conclusion here? The conclusion is we need to make certain modification of equation 4. That is the conclusion we can make at this stage. So, the conclusion from this treatment we can write here, some serious modification is required. Some modification is required in equation 4. The fourth Maxwell's equation, whatever the fourth Maxwell's equation we are having, some modification is required. Mind it, here we mentioned that the divergence of J is 0. So, I should like a small note here before concluding. So, divergence of J and then plus del rho del t, this is a continuity equation, so one of the fundamental equations is 0. So, divergence of J 0 means del rho del t equal to 0. So, for steady current, so divergence of J equal to 0 basically leads to a condition that del rho del t has to be 0, and that is for steady current. When we have the steady current, this condition may satisfied, but not always, not always. So, I would like to conclude here in today's class, and in the next class we will discuss what kind of modification really required in equation 4. So, we should consider this equation is under scrutiny, that we find that some problems are having in this equation, in equation 4, and we need to put this modification in equation 4 such a way that left hand side and right hand side are compensating each other, they are complementing each other. If the left hand side is always 0, we should make the modification in such a way that the right hand side should also gives the value 0. So, with this note I like to conclude today's class. So, in the next class we will discuss more about Maxwell's equation. We find that there is something very interesting called the displacement current, and we are going to include this displacement current, and by including this displacement current we can solve this issue. So, that part we will do in the next class. Thank you for your attention and see you in the next class.